So we'll go ahead and get started. Hi, everyone. Thanks for taking the time to come to this session. My name is Abhinav Gupta. I'm a program manager on the Windows Device Connectivity Group. I also have with me Elaine Mouchad, who's a senior developer on our team. And we're here to discuss about integrating Bluetooth on low-power buses. So what's the motivation for this? Well, an increasing number of PCs are being designed for lower power consumption to further enhance battery life and to enhance mobility as well. It turns out that transport connectivity of peripheral devices, for example, Bluetooth controllers, can play a key role in achieving higher energy efficiency. More specifically for Bluetooth, this means providing for transport connectivity options beyond just USB. Why is that? So I'll actually start off this discussion by highlighting some of the challenges that we faced when looking at this market space and how these translated into some of the goals that we set out to achieve. I'll then showcase some Bluetooth experiences on a few ARM-based platforms and try to demo what achieving these goals really looks like. I hope at that point you'll all want to know how you can integrate this into your own systems. So we'll go ahead and go through a design exercise and build a sample PC targeted for lower power consumption. By the end of the talk, we'll have developed for Bluetooth connectivity using low-power transports, and I hope that you can walk out knowing the implementation flexibility that we're providing based on your vendor-specific customizations. Now, it turns out that there are many challenges when we looked at the low-power market space. So traditional PCs usually connect over USB dongles for Bluetooth, at least what we had in Windows 7 support, or the internal radio is connected over a USB bus. Now, when looking at these more power-efficient designs, Bluetooth controllers over USB really pose some challenges for us, really calling for lower power transport connectivity. So what are some of these challenges? Well, one key challenge is that USB controllers on these platforms are actually quite limited and mainly targeted for higher bandwidth applications. This comes with some power implications. So as we'll see during this discussion, that we're enabling a transport extensibility model, so you can go ahead and choose the particular transport based on your hardware requirements. Now, it turns out that Bluetooth controllers using low power buses have a set of their own challenges, mainly in that they rely heavily on vendor-specific customizations, something that we really haven't seen on the USB front. So as we'll see again later on in this discussion, we're enabling implementation flexibility so you have an easier time integrating these vendor-specific customizations back into our stack. Now, I've been talking about power and power. What about performance? Well, performance plays a very key role in delivering high-quality user experiences. Now, we wanted to make sure that our app developers can focus on those great set of unified, higher-layer experiences without needing to worry about the underlying transport connectivity. So the way we've designed our stack, and you'll see this later on, is that higher-layer applications really do remain completely transport agnostic. Now, one scenario in which performance plays a very, very important role deals with voice. So think about a voice over IP-based application using a Bluetooth headset. Now, it turns out that there's very strict latency requirements that can get quite challenging to meet using these low-power buses. So we'll see later on that we're enabling this voice-based offloading channel or sideband channel that should help deliver optimal audio quality for your experiences. And again, with our stack keeping higher-layer applications transport agnostic, you as an app developer can really focus on delivering those end-user scenarios. So let me now sort of show you some demos based on some of the collaborative work we've done with our partners. I'll actually use my sister, who's a doctor, as an example to walk through these. So a typical day for her starts off with going through patient rounds in the mornings, getting in and out of surgeries in the afternoons, and then having to fill in her clinical reports at the end of the day. Now, at the same time, she's a very avid music listener and loves listening to her music when she's sort of filling in these clinical reports because things can kind of get mundane. So anyways, a low-power, ultra-portable based form factor that sort of allows her to remain productive and allows her to use those productivity applications while also letting her use that same entertainment device for her music listening purposes would perfectly meet her needs. So here we have a Qualcomm-based tablet. Now I realize it's not running that Metro UI layer. It is running Windows 8. It's just a previous version from the developer build that you guys all got. Now, what I'm going to show you is some use cases for Bluetooth. It's connected. This Qualcomm tablet is connected to a Bluetooth keyboard here, right? So I'm clearly moving around and able to have that responsiveness. Let me go and play some music. So we see music playing very well by itself. We've got the responsiveness of the keyboard and the mouse. Now, I can sort of, be typing, right? So we really see multiple profiles being used concurrently without any performance drawbacks. Audio quality is pretty high, so my sister can enjoy her music glitch-free. Now, the keyboard and the mouse responsiveness is also pretty high, which means she can be really efficient in those productivity tasks that she needs to be, right? Now, most importantly, right, Bluetooth is allowing her to be fully, wire-free, mobile, listening to her music. And when she really needs to focus and get down to her productivity tasks, she can, pause her music, dock this near her workstation and use her keyboard and mouse right away. And when she's done, she can go ahead and play that music back again. So this was the Qualcomm tablet based on their dual-core Snapdragon architecture. I also have a TI-based tablet. This is their OMAP 4-based tablet. It's the exact same set of experiences. I've got an actual mouse here. So we can sort of see the mouse movement. Here's our keyboard working as well. And if I go ahead and I play my music, right, I can sort of, again, benefit from my mobility that Bluetooth is offering and the multiple profile usage without any performance drawbacks. Now, I'd like to highlight that both of these platforms are using high-speed UART as their controllers. Now, from a very first glance at this, you might be wondering, how is this any different than what we're offering on traditional PCs with USB-based controller connectivity? So in terms of scenarios, you're right. There really isn't any much difference. And that has to do with how our stack really keeps those higher-layer applications transport agnostic. Now, in terms of power and performance, we'll take a look at some numbers later on in this discussion to really see how those two compare, UART and USB. But before we do that, let's take a look at how we can achieve this. So here's a look at our Windows 7 Bluetooth stack. We used to have only support for USB-based connectivity. BTH port there is our core driver implementing L2 cap and SCO layers. BTH USB.sys is our USB mini port driver in charge of actually implementing the USB-specific functionality. Below that, we've got USB port driver. It sort of handles the USB-specific power management, data I/O, and kind of denotes sort of the USB stack there for us. And below that, we've got the Bluetooth controller. Now, with USB being a system-based bus, enumeration is done via plug-and-play, PNP, and our inbox profile support used to be what's listed there. So what's new in Windows 8? Right? So we still have BTH port and our BTH USB controller support. Nothing's sort of changed there. But we're also enabling for transport connectivity beyond just USB. How? Well, we have this component called bthmini.sys. It's an extensible transport driver component below which a Bluetooth transport driver that comes from our partners gets plugged into. The Bluetooth transport driver is specific to a particular transport, for example, UART in this case. And basically, our BTH mini component has public interfaces below it, so your driver can plug right into it. Now, both of these components together are sort of the equivalent of BTH USB. Below this, we still need controllers for data I/O, managing our power, for our power up and idle wake signaling. So we sort of rely on these controller drivers, and we'll get into exactly what this means in a little bit. These controller drivers now are sort of equivalent to the USB port driver. Now, with many low-power buses being non-system bus-based, enumeration is done via ACPI, and we'll see what really that is and how that can benefit you by being able to really declare your device properties and interconnection dependencies later on. We'll also see how ACPI will help you share the same driver across different platforms. So if you're an IHV looking at integrating your Bluetooth controller into several different platforms, we think this will really help you out there. So I mentioned earlier that we were going to go through a sample design exercise, and the reason for that is the previous stack diagram was a very abstract view of our stack because we hadn't really chosen any specific transports. So let's go through that exercise and build a sample system. So here we have a Bluetooth controller. as a designer, I need controllers for data I/O, power on and off, and also for idle wake signaling. So there's lots of options out there. Something that we've seen quite a bit, and something that is sort of applicable to this exercise, I'll go ahead and choose the following. So we've got high-speed UART being used for that data I/O component, I2C for power delivery, and GPIO for my power management. Now let's go and take a look at what our stack diagram really looks like. So before actually integrating all those controllers into our stack, we need to first declare what the device dependencies are and how they're really related to each other. So here's a device description of the Bluetooth controller. We see sort of the hardware ID up there. This is what will show up in Device Manager. We also see that there's controller device properties for UART, I2C, and GPIO. And I've sort of abstracted away the I2C GPIO for ease of reading. But let's take a look at the UART component. So we can declare things like the initial baud rate. That's denoted as the 115.2 kilobits per second. You can also denote things like our FIFO sizes on the transmit and the receive sides. That's the 480 and the 32. Now, I'd really like to sort of focus on this resource name, right? So that's denoted as the UR1 component there. So it may turn out that there's several UART controllers on a given platform. So the resource name really helps us specify which of these UART controllers our Bluetooth radio is going to be connected to. Now, I mentioned earlier, as an IHV, you may be integrating your Bluetooth controllers into several different platforms. So you can really use ACPI to denote the resource dependency differences. So maybe there's a different baud rate that the UART controller comes up as. Maybe there's a different resource name that UART controller is tied to for your Bluetooth radio. You can do all of this in ACPI directly and sort of just develop your driver once and perhaps use it multiple times across different platforms. So once we've declared all these resource dependencies and how our radio is really connected in the system, let's take a look at how this reflects back into our stack diagram. So it's the exact same stack diagram we saw earlier. And we sort of removed the BTH port and USB aspects of it because that's not the focus here. So now we have dependent controller drivers for UART, I2C, and GPIO. So when we looked at sort of system implementations, it turned out that UART, I2C, and GPIO controllers can significantly vary from implementation to implementation. That makes it pretty challenging for us to deliver a class driver. However, to ease your integration and your development time, we're providing WDK samples for each one of these, as well as a class extension manager that will help you extend and enhance these samples based on your hardware-specific needs. Now, the Bluetooth transport driver becomes a Bluetooth UART-specific transport driver because we've chosen that as our transport. Again, when we looked at systems, this varied significantly from system to system. So again, same challenges around our class driver support apply there. So again, to ease your integration and development time, we have a KMDF WDK sample, which you can also enhance for your particular vendor-specific implementations. Now, the WDK sample we have is UART-based, but again, you can adopt it for any other transports as well. In addition to just transport, you can also incorporate for things like device-specific configuration, also for your power management specific implementations that you have pertaining to your Bluetooth controller in this driver as well. There's also two topics that I really haven't touched base on yet, which is this support for combo chip support and radio on-off. We'll get into the details of each of these later on as the next part of this discussion goes into each four of these individual concepts. So let's start with device configuration. So now device configuration really involves setting up the Bluetooth controller for use. Now this may be setting a higher baud rate. Remember, we had that initial baud rate as 115.2 kilobits per second. Turns out that Bluetooth requires a slightly higher throughput, typically in the range of 3 to 4 megabits per second. So that can be done via the device configuration aspect. Another thing that we see often being done is specifying the Bluetooth radio's hardware address. So you can do all of this in device configuration. Basically, everything that the Bluetooth controller requires to set up for full functionality. Now, when we were looking at the market space out there for these low power-based Bluetooth controllers, it turned out that device configuration is mostly done via vendor-specific commands. To enable implementation flexibility, you can either do and incorporate for this initialization directly into the transport driver or as part of a separate function library. Our WDK sample shows you an example of each one. So that should hopefully help you integrate with a little bit of ease. So that's device configuration. The next topic is power management. So here are the 3 states that our core stack supports. It's active, low duty cycle, and off. The D there sort of relates to device states. So these are D0, D2, and D3, respectively. Now, I'd like to really emphasize that in order to achieve for power efficiency, we want the Bluetooth controller to go into a low power state when there's no Bluetooth activity going on, but be able to quickly resume back to D0 when a user wishes to use a Bluetooth device. I'll actually use a keyboard-based scenario to walk through some of these state transition. So let's say I'm actively typing on my keyboard. We're in D0. Let's say after a while, I'm either thinking or taking a break, and I stop typing. So idleness gets detected by our stack, and we transition into D2. We inform the controller that you can go down into a lower power cycle. When I start typing again in D2, our stack quickly resumes back to D0, informing the controller to go back to active so he can feel free to service that device request. Now, again, remember, we want the controller to go in a low power state and be able to resume as quickly as possible. The other thing I'd like to mention about this diagram is both of these states we just talked about are in the context of system active state, or S0. Now, if I decide to hibernate or sleep my device, right, we go into S3 or S4, we can actually move into a lower power state. Our stack can go into D3, and we can inform the controller to go into the off state. So this was a representation of what our software stack does in terms of implementation. You can sort of translate this into your hardware by performing the appropriate signaling. How? Let's take a quick look at a sample implementation. So here's the exact same diagram for the system that we were trying to build. We'll sort of walk through a couple of power cycling scenarios. So walk through the power up sequence from a cold boot. So the first thing that happens is the I2C component would go ahead and power on the Bluetooth controller via the power management IC, or the PMIC. That will go ahead and send power directly to the Bluetooth controller. Now, the Bluetooth enable line would get asserted. Putting the Bluetooth controller in active, I start typing on my keyboard. Our stack is in D0. Now, let's say I stop typing for a little while. Our stack is going to detect that idleness. So what will happen is we'll go into D2. We can inform the controller to go into a low power state. This can involve the Bluetooth enable line getting deasserted. Maybe this is the indication that you guys use on your implementation for going into a lower power state. At the same time, this host wake line would get armed for wake. Remember, I want to be able to wake up my device from that keyboard if I hit a key, and that's the exact reason we're arming that for wake. Let's say after a little while, I actually do hit a key. What happens is there's a signal that's detected on the host wake line. Our stack quickly jumps back to D0, and we send back that Bluetooth enable signal down to your controller, and you can go ahead and resume back to active. Now, we've seen sort of the software stack implementation of what we're doing for power management. And we've sort of seen how the translation happens over in hardware. How does the software and the hardware get bridged together? Well, you can do this, in your transport driver. Now, we have some documentation that's going to be made available to you pretty soon, so you can actually walk through a couple of examples and pertain it to your vendor-specific needs. So now, I mentioned earlier that we were going to go through this concept of combo chip support. So we're starting to see more and more radios getting integrated onto the same die. And more specifically, we're seeing that oftentimes Bluetooth, FM, and GPS are using and sharing the same transport. So now we have a multifunction device. It's a Bluetooth, FM, GPS device. Say it's still using the exact same transport, still the UART, I2C, and GPIO. So that Bluetooth transport driver now becomes a UART bus driver, able to enumerate our FM and GPS stacks, respectively. We think that this will help you accommodate for changing hardware configurations and really help you by delivering only a single driver across different functions that you might introduce later on down the road. Again, our WDK sample shows you an example of where and how this is possible. So if you do have a multifunction device later on in the future, you're more than free to use that implementation. Now, in addition to combo chip support, I mentioned this concept of radio on-off. Now, there's been a big effort across all of Windows 8 for a new unified radio management experience. More specifically, it's the ability to control the power and toggle the power of all the different radios on your system via a single software switch. So we're actually delivering the Radio Manager, which is a UI layer. Basically, it enables a unified experience across all these different system radios on your particular platform. When you plug in your vendor-specific DLL for the Bluetooth component, you'll automatically benefit from this unified UI experience. Again, our WDK sample shows you an implementation of how you can plug in the lower edge of this DLL into the bus driver. So if you have any development issues, that should also help you out. So I've been focused on sort of the higher layer or the lower layers of our stack. What are we doing in terms of profile support? So here's a quick look at some of the inbox profiles that we have. And now we're also allowing for our partners, as we did in Windows 7, to be able to deliver additional profiles on top of our stack. Now, at the very beginning of this discussion, I mentioned that there were some challenges that we face in terms of voice-based scenarios, specifically to do with performance. So this is sort of that HFP profile, the hands-free profile. So given these challenges that we're facing, there's some additional work we've done. So let's take a really quick look at what we've done here. So now, I mentioned that voice has some very strict latency requirements. And we don't have to worry about this on the USB front because USB has this concept of an isochronous channel that helps us ensure on-time delivery. Now, many low-power buses don't really have this prioritization or this concept of going directly over your HCI for guaranteeing on-time delivery. So what we've seen in system designs is really this concept of an alternate I2S channel that exposes itself as a PCM endpoint to help mitigate that and guarantee that on-time delivery of audio. So in terms of the stack implementation, the Bluetooth stack, right, the core stack, basically acts as the management path or the control path managing the audio channel configuration. So this would be opening, closing, and configuring those SCO channels. Meantime, the audio stack, which is the left half of this stack, is in charge of the actual data path. So that actually traverses all of the voice data that's going to go down. Now, we want our app developers to be able to sort of build those higher layer experiences and not really need to worry about these underlying complexities. So our HFP driver, what it does is it automatically goes into this quote-unquote in-band mode for USB, because remember, USB doesn't really need this concept of alternate I2S. And when it detects that there is a low-power bus, let's say it's a UART-based controller, it'll switch into this sideband mode. It's completely agnostic to our app developers, so you can still focus on those higher layer scenarios. Now, to keep driver development simple, our HFP driver exposes interfaces that are public so that your audio driver can plug directly into it. These interfaces are public and documented. There's actually a white paper that we have, so you should definitely be able to look at that and know how the implementation would work between the HFP driver and your audio driver. Now, we've gone through a pretty deep dive of what our stack implementation looks like, and I've been talking about power and performance. Let's take a quick look at some numbers. So now it turns out that we have USB and we've got high-speed UART controllers, and we're having these ARM-based platforms. So what our team did was we took one of these platforms that I demoed earlier on, and we ran through two different scenarios. One was receiving a file, and the other one was transmitting one. We used the high-speed UART internal controller first, and then we switched it out for a USB dongle that was externally connected. So here's some throughput and CPU utilization numbers that we've captured. We think that throughput is a very good metric for looking at performance, while CPU utilization is a good metric for looking at power consumption. So from a first glance, we're sort of seeing that for roughly about the same throughput, USB is sort of giving us slightly higher CPU utilization. Now, these are some very initial numbers that we've captured. We are doing more investigations to make sure we can optimize further. Now, again, we've gone through our stack implementation, and I'd really like to reiterate that we're building a platform so you can truly develop a solution for your unique hardware needs, right? So what we really ask for is your help in following our certification guidelines that we have in our certification kit, and know that you're going to benefit from these tight integration of our stack in regards to power management, and also that we're still enabling for innovation so you can develop additional profiles on top of our stack. So when our certification kit does become available, please take a look at it and follow the guidelines that we have in there. So with that, I'll sort of close out this discussion by highlighting some key remarks. We developed for Bluetooth connectivity using low-power transports. We saw that our stack is really enabling this ease of flexibility for you around your choice of transport, around your way of incorporating device configuration, managing for power up and idle wake signaling, as well as accommodating for changing hardware configurations in the future. I'd like to definitely reiterate that we also saw how easy it is for you to go ahead and take integration as part of our stack and still deliver those high-quality end-user experiences. As a reminder, take a look at our certification kit and follow the guidelines there, as well as taking a look at these following guidelines that we have around Bluetooth bring-up support on low-power buses. So this includes a proper ACPI table description, working to develop a transport or bus driver. Take a look at our sample, take a look at the documentation that we have. Remember to also work with your IHVs or your partners to work on those dependent controller drivers, as well as your partners around providing support for audio drivers so it can play very well with our HFP component. Now, there's also a set of really exciting sessions that are happening related to this talk. I think the first two have happened yesterday, so if you missed out on those, please follow them up on webcast. The third one is scheduled for happening tomorrow. I highly encourage all of you to go into it because we're really going to be talking about these new set of Bluetooth low-energy devices and how they can connect into our stack. Hopefully, you'll definitely see something that you haven't seen before. And I also mentioned some documentation that we have that's made available. These should be available to you soon, if not already. Again, this goes into our extensible transport driver components. It goes into some of the other additional radio management features that we've added. So take a look at that in your development needs. And with that, I'll sort of close out my talk. And I'd like to thank all of you again for giving me a chance to present our Bluetooth controller support on low-power buses. Can't wait to work with you. Thank you. We'll sort of be around here. Elaine and I will be here, so if you have any questions, feel free to just come up and talk to us. Thank you.